This video deals with titration of a strong acid by a strong base. And there are several questions that we can ask about this type of titration. And so in this first question, we want to know how much potassium hydroxide needs to be added to reach the equivalence point. And then what we'll do on the other slides is calculate the pH at different points along the titration curve. So in order to find out how much potassium hydroxide is required to reach the equivalence point, I need to remember that at the equivalence point, the moles of acid that I started with is equal to the moles of base that I added. And so I know the volume and concentration of the acid, so I should be able to use the molarity equation to find the moles. And then I know that at the equivalence point, that is a point where the moles of base I added is equal to the moles of acid that I started with. So I know how many moles I need to add, and I know the concentration, so I can use the molarity equation again to find the volume of potassium hydroxide that I need to add. So for the acid, to find the moles, I'm going to use that molarity is equal to the moles over the volume. And then I'm going to rearrange that, multiply both sides by V, so I get that moles is equal to the molarity times the volume. And so for my acid, my molarity is 1.50 moles per liter. I'll multiply that by the volume. So 50 milliliters, I need to convert to liters. So 0.05 liters. And so I have 0.075 moles of acid. So to get to the equivalence point, I need to add that same number of moles of base. And to find the volume, I'm again going to use the molarity equation. So molarity is moles over volume. Only now I need to first multiply both sides by V. So it becomes M times V is equal to N. Then divide both sides by M so that I get volume is moles divided by the molarity. So the volume of base that I need to add is 0.075 moles divided by 2 moles per liter. So the moles cancel, and I've got 1 over liters. So my answer will be in liters, and I get 0.0375 liters. Or if I want to convert back to milliliters, that's 37.5 mLs. All right, so we'll go to the next slide and do another example. All right, so the next question they're asked is, what is the pH before the addition of any base? So what they're really asking is just, what is the pH of 1.50 molar HBr? Because I know this is a strong acid, it completely dissociates. So I know that pH is the negative log of H3O plus. Now the concentration of H3O plus will be the same as concentrations of my strong acid. So it's the negative log of 1.5. And I get a pH of minus 0.176. Now remember that the pHs are usually between 0 and 14, but if I have a strong acid that has a concentration greater than 1 molar, then I'll end up with a negative number. All right, the next question that we're asked is, what is the pH after the addition of 15 milliliters of potassium hydroxide? So I need to know the chemical reaction that takes place between my strong acid and strong base. Now remember, HBr is a strong acid, so it completely dissociates. So what I have in solution is not actually HBr. What I really have is H3O plus and Br minus. Br minus is neutral, so it doesn't have any effect on the pH, so I can ignore it. So what I'm concerned about for the strong acid is that I really have H3O plus. And potassium hydroxide is a strong base, so it also completely dissociates. So what I don't have in solution KOH, what I have is K plus and OH minus. But it's the OH minus that I'm interested in. So in my equation for the titration of a strong acid with a strong base, I like to write it like this, because it's more accurate of what's actually going on in the solution. So I've got H3O plus from the strong acid, I've got OH minus from the strong base, and so those will neutralize each other to form water. All right, and so these titration problems with a strong acid and strong base are just stoichiometry problems. So remember, when we do stoichiometry, we need moles. And I like to build a little table to keep track of what's going on. It looks kind of like an ice table, but it's not exactly an ice table, so I like to call it a before, change, and after the reaction table. So to get the moles of acid, we actually already did that in the previous problem. So I know that I have 0.075 moles of strong acid. And that starting amount of acid will be the same in all of these problems. To find the moles of base, I just use the molarity equation. Right, and I need to rearrange that so that moles are equal to the molarity times the volume. So I have 2 molar strong base times 0.015 liters. I have to convert the milliliters into liters. And I get 0.03 moles of base. So that goes here in my table. All right, so now I need to decide what the limiting reagent is. So I've got 0.075 moles of H3O plus. I've only got 0.03 moles of hydroxide, so the hydroxide is my limiting reagent. So unlike ice tables where I don't know what the change is going to be, in this case I know the change when I do stoichiometry is due to the limiting reagent. And the water, because it's not going to affect the pH, I don't really worry about that. So my change for both hydroxide and H3O plus is 0.03. So I'm left with no hydroxide and 0.045 moles of H3O plus. So now to find the pH, I know the moles of H3O plus, and I know the volume. The volume is the 50 milliliters of acid that I started with, plus 15 milliliters of base, so I can find the concentration of H3O plus. Don't forget to add the volumes. So 50 plus 15 is 65. Convert that to liters. 0.065 liters. And I get a concentration of 0.692 molar. All right, so to get the pH then, I just take the negative log of that. And I get a pH of 0.160. Okay, on this next slide, we want to know what is the pH after the addition of 37.5 milliliters of potassium hydroxide. And so I've gone ahead and drawn the reaction in the BCA table. And if you remember from the very first problem, we already calculated that the equivalence point is reached when I add 37.5 milliliters. So we don't really need to do a calculation in this case. At the equivalence point for a strong acid, strong base titration, the pH is going to be 7 because all of the acid is reacted away by the base that I've added, so they've completely neutralized each other. But we'll go ahead and go through the calculation and see why the pH comes out to be 7. So again, the moles of acid that I started with doesn't change. So I just need to find the moles of the strong base. So again, I'll use moles is equal to molarity times volume. So I've got 2 moles per liter times 0.0375 liters, and I get 0.075 moles. So I put that in for the OH. Right, so we can see that sort of they're both the limiting reagent, right? They're going to completely react with one another. So minus 0.075, minus 0.075. So I've got no strong base left. I'm sorry, no strong acid left, no strong base left. And so they've exactly neutralized each other. And so the pH is going to be 7. so anytime I have a strong acid, strong base titration, the pH at the equivalence point is going to be 7. All right, we've got one last example. And so in this case, we want to know what is the pH at some point after the equivalence point. And so I've got my same chemical reaction, same initial moles of H3O+. So again, I'll find the moles of base. So the molarity times the volume moles. All right, so now the H3O plus is the limiting reagent. So I'll have no H3O plus left and 0.025 moles of hydroxide. All right, so now to calculate the pH, I'm going to use that I have hydroxide left over. And so the concentration of the hydroxide, because remember in the table, that's not concentration, that's moles. So molarity is moles over liters. I need to use the total volume. So I started with 50 milliliters of acid. I added 50 milliliters of base, so I have 100 milliliters, or 0.1 liters. So the concentration of hydroxide is 0.25 moles per liter. And so I can find now the pOH. So for the pOH, I get 0.602. So then the pH is just 14 minus the pOH. And for pH, I get 13.398.